right, our topic is telescopes. Aside from robotic probes that have been sent to explore our solar systems and other nearby planets, astronomy is all about telescopes. At least the observational side is. They're our #1 source of information about the solar system, the galaxy, the universe. This is what we need to talk about. So, what is a telescope? How do they work? What's the idea here? So what is a telescope? Well, first of all, telescopes were invented probably in the year 1609. They were first invented up in the Dutch Republic. The United Provinces of the Netherlands, which at the time was one of basically the freest country in Europe, had the greatest amount of freedom of speech, religious freedom, commercial freedom. The first stock exchanges were there. All kinds of wonderful, amazing scientific and cultural developments happened up in the Dutch Republic. The great astronomer Christian Huygens was up there. And shoot, the Constitution for the United Provinces of the Netherlands was a big inspiration for the United States of America. The United States of America, United Provinces of the Netherlands, that's not a coincidence. The founding fathers of our country were strongly inspired by this vision of a very free country over in Europe. And our first constitution, the Articles of Confederation, which we operated under during the Revolutionary War and stuff, was based on their constitution, and then we threw it out and wrote our own. But anyway, so lots of wonderful stuff went on there. Up in the Dutch Republic, the telescope was invented. Telescope invented. Of course, the first telescopes were very, very simple, 2 or 3 power spyglasses of Astemi-Hardys we see, pirates and stuff like that. So they were for ships at sea to look for enemies and things like that. Very quickly, down in Italy, Galilei discovered this and then worked out the mathematical principles behind a telescope, built his own, was able to build much more powerful ones, far more powerful than the little spyglasses that were being manufactured up in the Dutch Republic. And then the other big thing is he not only showed the designs to some commercial people who were shipping things around, but most importantly, he pointed his telescope up at the heavens. And then he wrote books about it. He wrote his whole book, the Starry Messenger, where he described all the wonderful, amazing discoveries he made. So, all right, so let's talk about Galileo's first telescope. What did this look like? The first astronomical telescope was a refracting telescope. It's made of 2 lenses. Bigger lens in the front, smaller lens in the back. The bigger lens is called the objective lens. And this over here is the eyepiece lens. Eyepiece. So that's how it works. There's the objective lens, there's the eyepiece. The simplest telescope, Galileo's first telescope, had only 2 lenses. This is called a refracting telescope because it's made of lenses. The objective lens, the objective is a lens. We'll talk about the other type in a minute. And so then it's like, well, what's the purpose of a telescope? Why do we need telescopes in order to observe the universe? And the answer is, the reason why we need telescopes, most people think, ooh, it's magnification. The stuff we're looking up there is really small. We want to make it bigger. That's true, but if I were to list out, I would list out 3 functions of a telescope, and I would say that's the least important one. So we're talking a refracting telescope, and so now we want to talk about, so there's a diagram and all this, and now we want to say purposes of a telescope. I'd say 1, 2, number 3 is magnification. And that all takes place, that's determined by the eyepiece. So if you ever have a telescope, you don't like the magnification, you screw out one eyepiece, you pop another one in there. Most telescopes have many different eyepieces. You come with another eyepiece costs, $30, $40, $50, $60. It's not that expensive. So the magnification, that's all about the eyepiece. The main function of a telescope, the reason why we build telescopes, are to gather light. the things we're looking at are not, okay, they're small, but the main thing is they're faint. We want more light. We want to get as much light as possible. When you look up at the stars and the planets and the heavens with your eye, you are limited by the size of your pupils. Now, the human pupil can expand a little bit when it gets dark, and so that helps, but there's a limit to how much light you can get in there. If you could take your pupil and stretch it out and cram it up and so pull it out to a much larger size, then that would hurt a lot, but it would also allow more light to get into the back of your eye. So in a sense, that's really what a telescope's all about. It's a light funnel. It takes light spread out over a large area and gathers it together so to take this huge amount of light and bring it all into your pupil. The other main thing is to resolve detail. Solve detail. To try to get as much detail as possible on this. If you just magnify a bad image, that doesn't really help you. No, you want to improve the image quality, and that comes from getting light over a wide area. So resolving detail and gathering light both go together. If you have a larger objective lens, then you're going to bring in light from over a wider area. So these both come from having a large objective lens. So that's a huge thing. The bigger if two amateur astronomers are comparing their telescopes, what do they compare? They compare how big the diameter of their objective lens, and then the bigger one wins. It's bringing in more light, more details, making things brighter, being able to bring more things. And then magnification, if you don't like your magnification, you put in a new eyepiece. So never buy, if you ever see a telescope advertised, this has 200 power or something like that, don't buy that. Magnification is not what the key part of a telescope is. That's easy to change. The hard part is how big is that objective lens or mirror. So we got Galileo and his refracting telescope. Isaac Newton developed the reflecting telescope. Reflecting telescope. So with the reflecting telescope, now the objective is no longer a lens, now it's a mirror. So I put a curved mirror out here at the back of this. So here's the objective mirror. And so the light comes in like this. It bounces, the curved mirror gathers the light together. Things bounce off a little secondary mirror here and then sends things out to an eyepiece. So the eyepiece is out here. So Isaac Newton developed one of these, built these. There are some other designs, and the idea was floating around. And so there are two main types of telescopes. So there's the refracting telescope, which bends the light with an objective lens, and then there's a reflecting telescope which reflects the light, gathers it with an objective mirror. And today, large professional quality telescopes, the big ones that astronomers use to do serious observations, are all reflecting telescopes. Why? Well, several reasons. First of all, when you're refracting light, when you're bending light with a lens, well, a lens acts a little bit like a prism, so it tends to spread out the colors a little bit. And so when I look at a star through my telescope, I can get a little bit of kind of a rainbow around the star. This is called chromatic aberration, and it's bad. We don't like it. You can play fancy games with your glass and maybe make things better, but it's a challenge. It's hard for refracting telescopes. No problem with reflecting telescopes. All light bounces off a mirror in exactly the same way, whereas red light is bent more than blue light, and so the amount that light's bent varies by color. Reflection is reflection. Here's another reason. Okay, so we're talking about reasons why big telescopes are reflectors. Okay, so one is no chromatic aberration. Here's another thing. If I have a refracting telescope, make it based on lenses, well, that means the light goes through the glass. Since it passes through the glass must be of very, very high quality. No bubbles in it, no fluctuations in density, or that'll mess everything up. On the other hand, with a reflecting telescope, well, you still have glass, but then you just coat the surface of it to make a mirror, and the light doesn't go through the glass. It just bounces off the surface of it. So your glass does not need to be of as high a quality as long as the surface is shaped fine. If you have bubbles deep inside it, who cares? So glass doesn't need to be as high quality. Here's another issue. If you have if you have a lens, well, you got to hold the lens around the edges. Otherwise, you can't hold it from the back. Otherwise, the light can't go through it. And if you make a really big lens, as people started doing in the 1700s, and starting finding that the bigger your telescope was, the more you're seeing, the more discoveries you're going to make. And they found that, well, if you make a really, really big honking lens there, and you're only holding it around the edges, well, then the center of the lens will actually sag over time. On the other hand, if you have a mirror, you can support the, since so you can hold it on the bottom side, and so the glass does not sag over time nearly as much. It can be held together in a much, much better way. So that's spectacularly useful. So those are reasons why big telescopes these days are reflecting telescopes. And now what we need to do is we need to talk about why. Let's see, why do astronomers, professional astronomers, put telescopes on mountains and into space? Usually when I ask this question, people say, well, be closer to the stars, be closer to the planets and the sun and all that. And that answer is completely, totally, 100% wrong, because being closer by a couple miles, forget it. You're talking about stuff was ridiculously far away. It is not to be closer. The answer, not to be closer, the answer is the air. The air is a horrible thing from an astronomical perspective. The air, if you were to take the air and compress it to the depth of, to the density of water, it would be like, several yards thick. So imagine trying to see the stars through water, through the bottom of a swimming pool, several yards thick. And that's what causes the stars to twinkle in the sky. It's all this air between us and space. Astronomy would be so much better if there was no air at all. So write your congressman and have air abolished completely. We would all die of asphyxiation, but man, we would see the stars beautifully. Once you get a couple miles up in, on top of a mountaintop, you can see things so much better. And that, the ultimate gold standard is go to space. Once you're 100 miles, 200 miles up, you're above the atmosphere, and then you can see a crystal clear, just wonderful, wonderful image. That's why the mighty Hubble Space Telescope is fantastic. And then, of course, we have all these other types of telescopes, like X-ray telescopes and ultraviolet telescopes and infrared telescopes, where we're looking at types of light which does not make it very well through our atmosphere at all. And so it's not to be closer to the heavens, it is to get above the air. Air, which is bad. Air is evil. Okay, so that's the key thing there. Now, there's some modern things that can be done. With big telescopes, we found some ways to adapt the shape of our telescope lenses in real time. As the ripples in the atmosphere are up there, we adapt the shape of our telescope mirrors in order to compensate for that. That's called adaptive optics. It's awesome. It's wonderful. It's a big new frontier in astronomy, as we can get some of our ground-based telescopes are doing things almost as well as the Hubble used to do when it first went up. But still, the gold standard is go to space. If there's no space, there's no air, and you've got a great view of the universe. So there's a quick introduction to telescopes.